But usually Maven loses its signal whenever it goes behind Mars, and it does that several times a day, and it comes back from the Mars towards our side, and then signal comes back. But this time the signal didn't get restored. Now it is going towards Jupiter, and we need to see how 3I can navigationally go fast. It is going to fly because of the speed it is flying so fast. It's not going to get attracted by Jupiter. But we need to wait and see how that whole thing is going to get turned out. It's a very interesting comet to watch.
Interest in 3I/ATLAS is already fading, but that may be the most premature mistake surrounding this object. Despite the growing narrative that its moment has passed, 3I/ATLAS has not exited the solar system. It is still traveling through it, moving toward one of the most gravitationally and strategically significant regions in planetary science, Jupiter's Hill radius. This is the vast boundary where Jupiter's gravity overtakes the Sun's influence, and natural staging ground for spacecraft, probes, and access to Jupiter's moons. Historically and theoretically, this region is exactly where one would expect deliberate navigation or long-term orbital interaction to matter. Yet much of the discussion has shifted toward closure, as if the object has already revealed all it has to offer. Mainstream explanations have increasingly leaned on familiarity, labeling 3I/ATLAS as nothing more than an ordinary interstellar comet exhibiting standard cometary behavior. The problem with that framing is that one of its most prominent and persistent features behaves in a way that directly contradicts the basic physics governing comets. Instead of a tail blown away from the sun by solar radiation pressure, 3I/ATLAS displays a pronounced anti-tail and a trailing coma, oriented in the wrong direction entirely. This is not a subtle effect or a momentary illusion. It is a sustained, well-defined structure that violates expectations formed from decades of comet observation and modeling. What makes this feature particularly difficult to dismiss is that it is not an artifact of a single instrument or observer. Amateur astronomers around the world independently documented the anti-tail using backyard telescopes, and their observations were later reinforced by data from the Hubble Space Telescope. This convergence of evidence places the phenomenon firmly in the category of physical reality rather than observational error. When an object behaves in a way that contradicts established models, the responsible response is not to downplay the discrepancy, but to investigate it further. The accumulation of unresolved anomalies surrounding 3I/ATLAS suggests that treating it as unremarkable is not caution, but avoidance. Avi Loeb's analysis begins precisely where the standard explanations begin to fail. Examining high-resolution images of 3I/ATLAS, he focuses on the anti-tail's length, brightness, and narrow collimation. In typical comets, dust grains released from the nucleus are small, often micron-sized, and their behavior is dominated by solar radiation pressure. These grains scatter sunlight efficiently, but are also rapidly decelerated and dispersed. This leads to broad, diffuse tails that fan outward and away from the sun. The structure observed in 3I/ATLAS does not resemble this pattern.
Loeb's calculations show that the anti-tail were composed of standard cometary dust. It simply could not exist in its observed form. Small grains would lose momentum too quickly under solar radiation pressure to sustain such an extended and sharply defined feature. The anti-tail would blur, shorten, and dissipate. Instead, what is observed is a long, persistent structure that maintains coherence over time. The only way to reconcile this with known physics is to assume that the particles involved are far larger than typical comet dust, likely millimeter scale or greater. These larger particles interact with sunlight very differently. They experience significantly less deceleration from radiation pressure, allowing them to maintain higher velocities and remain tightly grouped. This explains not only the anti-tail's length, but also its brightness and stability. More strikingly, the emission appears to originate from a narrow region rather than from the surface as a whole. This implies a collimated stream or jet, not the diffuse outgassing expected from an irregular rotating comet nucleus. At this point, the anti-tail stops being a curiosity and becomes a structural anomaly that resists conventional interpretation. The anti-tail alone would be enough to justify sustained attention, but it is only one piece of a much larger puzzle. When Loeb cataloged the full set of anomalies associated with 3IATLAS, a pattern emerged that went well beyond unusual dust behavior. What stands out is not any single inconsistency, but the sheer number of them, spanning trajectory, geometry, composition, brightness, polarization, and timing. Each anomaly can be debated in isolation, but together they form a narrative that is increasingly difficult to dismiss as coincidence. The object's trajectory is the first layer of improbability. 3IATLAS follows a retrograde path that lies within a few degrees of the ecliptic plane. Given the vast range of possible incoming angles for interstellar objects, such alignment is statistically unlikely. Its arrival timing compounded this improbability, bringing it into close proximity with Mars and Jupiter, while ensuring that its perihelion passage occurred behind the Sun, hidden from direct observation. At the precise moment when gravitational forces altered its trajectory most significantly, the object was obscured by solar glare. Perhaps the most striking geometric coincidence is its predicted close approach to Jupiter, occurring at a distance comparable to Jupiter's Hill radius. This is not merely a random point in space, but a region of immense dynamical importance. For natural objects, passing through this zone is possible, but rare. For an object exhibiting multiple signs of non-standard behavior, the coincidence becomes harder to ignore. Jupiter's Hill sphere is precisely where gravitational capture, orbital modification, or probe deployment would be most efficient.
2 weeks ago, I realized the arrival direction of 3IATLAS was within 9 degrees of the wow signal.
Directional coincidences add another layer. The incoming path of 3IATLAS lies within a small angular distance of the origin of the famous wow signal detected in 1977, an event that remains unexplained and is often cited as one of the strongest candidates for a non-natural radio transmission. While this alignment does not imply causation, it does add to a growing list of low-probability overlaps that invite scrutiny rather than dismissal. Jet behavior introduces further complications. The sunward-pointing jet persists both before and after perihelion, despite the object undergoing a gravitational deflection of roughly 16 degrees as it passed closest to the Sun. Maintaining a narrowly collimated jet through such a deflection would require either extraordinary stability or a mechanism not accounted for in standard comet models. Even more puzzling is that the jet appears to originate from opposite poles before and after perihelion, implying long-term thermal insulation of the night side or a level of structural symmetry that is rare among known comets. Composition deepens the mystery in ways that are difficult to reconcile with standard comet chemistry. Spectroscopic observations reveal unusually high concentrations of nickel in the gas plume, with nickel appearing in far greater abundance relative to iron than has ever been measured in typical comets. In known cometary bodies, iron-bearing minerals and silicates are common, while nickel tends to appear only in trace amounts, usually locked within solid grains rather than freely outgassed. The prominence of nickel in 3IATLAS suggests either exposure to extreme thermal processing, an origin in an environment with a radically different elemental balance, or a material structure that allows metallic elements to be released far more efficiently than expected. Compounding this anomaly is the apparent scarcity of water. Whereas water ice dominates the volatile content of most comets and drives their activity as they approach the Sun, 3IATLAS shows only a small fraction of water in its outgassed material. This inversion of expectations points toward either an unfamiliar formation region, far from the conditions that produce ordinary icy bodies, or an internal composition that does not resemble the layered ice-dust mixture seen in the solar system. Its optical behavior adds yet another layer of inconsistency. 3IATLAS exhibits extreme negative polarization, a scattering signature that has no close analog among known comets, and suggests an unusual surface texture or particle population. Near perihelion, the object brightened at a rate faster than any previously observed comet, defying models that link brightness increases to gradual sublimation of volatiles. Even more striking, its color appeared bluer than the Sun itself, a trait that implies atypical reflectivity or emission processes, rather than ordinary dust scattering. When these optical anomalies are considered alongside its inferred mass, the image becomes even more puzzling. 3I-ATLAS appears significantly more massive than earlier interstellar visitors, yet it moves through the solar system at a higher velocity. This combination challenges straightforward explanations based on low density or fragile structure, and instead hints at a body with either unusual material strength or a history that does not align with known populations of natural interstellar debris. Individually, each of these anomalies could be attributed to statistical chance, observational bias, or gaps in current models. Collectively, they form a pattern that strains those explanations. The probability of so many independent oddities aligning in a single object is low, and it grows lower with each additional inconsistency. At some point, the argument shifts from explaining anomalies away to explaining why so many exist in the first place. None of this constitutes proof of an artificial origin, and Loeb is careful to emphasize that point. What it does demonstrate is that the label ordinary does not fit comfortably. Science has a long history of progress driven by objects that refuse to behave as expected. From the precession of Mercury's orbit to the cosmic microwave background, anomalies have often been the first sign that existing frameworks were incomplete. 3I-ATLAS presents a similar challenge. It forces a choice between two approaches. One is to compress its behavior into familiar categories by smoothing over inconsistencies and focusing on superficial similarities. The other is to take the anomalies seriously, not as proof of extraordinary claims, but as indicators that something important remains unexplained. Continued observation, deeper analysis, and theoretical openness are not indulgences. They are the core of scientific responsibility. Whether 3I-ATLAS ultimately proves to be an exotic natural object or something entirely unexpected, dismissing it prematurely would be a loss. Objects like this are rare, fleeting, and rich in information. The real question is not whether 3I-ATLAS is artificial or natural, but whether we are willing to follow the evidence wherever it leads, even when it complicates comfortable narratives. In that sense, the story of 3I-ATLAS is less about what it is and more about how science chooses to respond when the universe does not behave as predicted.